Swayam Prabha. Digital India. Educated India.
Welcome to Module 5, Lecture 4. So far, we have looked into issues of fresh concrete and of course the production process. And in the last lecture of this module, we look at the two important aspects of handling fresh concrete, namely compaction and curing of concrete. So first we talk about compaction. Why do you need it at all? Then generally we use it vibrators, so something about the vibrators themselves. Then mechanism of fresh concrete under vibration a little bit, because we have discussed quite a bit of it elsewhere earlier. And then we'll talk about execution of vibration again briefly. And lastly, we'll talk about curing, need and method. So let's talk about compaction, and that's you usually do by vibration. Now I mentioned this earlier that placed concrete contains air voids up to 30%. If it is of course dry concrete, we are not talking about very highly flowing concrete or self-compacting concrete. And also we said that it seldom conforms to the shape of the form. So therefore compaction is required to drive the entrapped air out, to densify the concrete, and also to increase the homogeneity and uniformity. This has other benefits, but largely to entrapped air has to be driven out and concrete must be densified. So that's why we need vibration. This compaction is achieved of course by vibration. That's what we mentioned earlier too. Now concrete vibration, well, energy for compaction is supplied through oscillatory motion of vibration, which is nearly simple harmonic motion. We can measure the frequency of such vibration in air, but it's difficult to measure within concrete, though it is more relevant if we can measure the amplitude of this vibration. So energy of compaction is supplied through vibration, oscillatory motion of vibration, and it is generated by means of rotating eccentric having a frequency and amplitude of vibration. So it's essentially all types of vibrator actually in some kind, is basically moving eccentric, having frequency and amplitude generates the vibration, and this oscillatory motion which is generated, which is simple harmonic motion, causes air to drive out. We'll look into the mechanism of course. We can determine the frequency of the vibrating machine or whichever I use, the equipment, in air, but within concrete is difficult because the effect of the damping and other things, the interaction of the vibrator or vibrator component, which is vibrating component with the concrete, is difficult to measure the frequency there. Now we have generally two types of vibrator classification: internal vibrator and obviously external vibrator. But internal vibrator themselves are again classified into three types. We will not discuss all of them because it's not on machines, but most commonly used one of the internal vibrator is the flexible shaft type, right? Flexible shaft type. Other one is of course a vibrating machine, but the motor is handheld, and from there power is transmitted straight away to the vibrating component. Then there are air vibrators, which can also be internal vibrators. But the most common type is a flexible shaft type. Once in a while, you might see an electric motor in hand, and it's the rotating part or the eccentric, which actually provides vibration, is just connected to the motor. The external vibrator is foam vibrator, which vibrates the foam, and also I can have a vibrating table, generally used in laboratory or in precast, for precast elements. So you have a table which can vibrate, and you put your mold and the concrete, and therefore the vibration takes place there. Foam vibrators are relatively more common, but most common is of course the internal vibrator of the flexible shaft type. So let us see what they are. There are some surface vibrator used for floors, vibrating screeds, etc., which are floor vibrating for floors or flat surfaces, slab, etc., etc. Immersion or most common is the immersion type of vibrator, which are called immersion vibrator or submersible poker or spud type. They have flexible shaft, and other one is motor in hand type. Let us see quickly how do they look. This is the three types which can be there. For example, you can have a bearing here, flexible drive shaft, which is normally a spring which can rotate. Actually. A shaft itself is a spring which will be rotating, connected to a motor, and then there are the bearings, and this is the eccentric mass. So this is the eccentric mass or the eccentric shaft. There is a bearing here, and this rotates eccentrically. Causing oscillatory motion, circular oscillatory motion, and the concrete in the surrounding will be actually subjected to this oscillatory motion of the vibrator, which actually pushes the concrete somewhat, and then again it's released. So there's a kind of compression of the concrete, and then there is a kind of rarefaction, because this will be moving in simple harmonic motion. So this is one type. The second type is pendulum type, where the mass is here. The flexible shaft is here, which is actually, as I said, a spring. It's connected to the bearing, but there's a rod. There is again pendulum shaft. Now this pendulum shaft is connected to the mass, eccentric mass, and this eccentric mass again causes oscillatory motion, which rotates and causes oscillatory motion of the vibrating, of the needle that is there. So these are also called poker vibrator, needle vibrator. They have all flexible shaft, and here the motor is here. Electric or pneumatic motor is straight away here. So motor is here, is cable or hose simply. It is cable or hose. If it is pneumatic, then there will be air hose. So compressed air will come through this, and here is air will come, compressed, it will get compressed air. Eccentric is also similar. These are not very common. This is a very common type. Very common is this type, and even this may be quite useful. So this is how they work. Actually, the needle vibrator, as we call it. So this portion of this component of the equipment, goes inside the concrete and causes oscillatory motion around in the concrete around, which will be compressed and rarefied and so on and so forth, radially going outward, longitudinal waves, as well as it might be generating other kind of waves also, but largely it will be generating longitudinal waves and maybe some transverse wave too, but causes actually kind of oscillatory motion, spreads around over a circular radius of influence, over a circular area having a radius of influence. So what you do, you shift from one place to the other, and one place to the others, and then it's go on vibrating the concrete as they are. This is flexible shaft type is the most common. and its diameter can range from 20 millimeter to about 180 millimeter. So usually vibration is generated by means of rotating eccentric, as we said, having frequency and amplitude of vibration, and basically frequencies etc. is available, data is available. So dimensions are from 20 to 80, 180. Now we can look at this head dia of this needle, 20 to 40 mm. Where will you be using this? Plastic concrete, thin section, right? This will be, you will be using it in plastic concrete. P stands for plastic, T stands for thin section, and congested reinforcement. So here I have C stands for, P stands for plastic, T stands for thin section, and C stands for congested reinforcement. So you see, thin head dia 20 to 40 mm. 20 mm is used in thin section. For example, web of a let us say web of a box section, some web, thin box, thin web, about say 100 or 150 mm, 100 mm, 100 mm or 150 mm thick web, and you have a lot of reinforcement here, plus a pre-stressing cable is passing through. So it's a thin section. Now concrete has to be plastic, because if it's a dry concrete, you will not be using this. Now recommended frequency, of course, in kilocycles is given as 10 to a recommended frequency in kilocycles per minute. It's given in, that means 10 to 15,000 kilocycles per minute is the recommended frequency. And you can see as your diameter increases, this diameter increases, frequency reduces. So this is high frequency, this is lower frequency, all right. And average amplitude is low here, average amplitude is high here. So average amplitude is high, frequency will be low. Average amplitude is low, frequency is generally higher. So radius of action is 8 to 15 centimeter. In this one, radius of action is much more. So where you want to use, where you have a thin section, plastic concrete, congested reinforcement, you might use this. While this might be used in mass concrete, you can see its radius of operation is quite high, and compaction rate is also fairly high. So where you have large mass concrete, of course you want to vibrate it, then you might use massive section. You want to use this, for example, in dam. M stands for massive concrete, so mass concrete in dams you will be using. In between, if you see 30 to 60, very common is about 66 mm, somewhere around this. This is very common. Slump less than 75 mm, it's suitable for that kind of concrete, relatively stiff, not very stiff. This is absolutely plastic, maybe 100 mm slump, or less than, it's just below pumpable concrete, let us say. Pumpable concrete is quite flowing, but pumpable concrete itself, if you are compacting, then it should be used. You can use this also. But in thin section, larger section, of course, you can use this one. So plastic concrete, wall, column, beam, you can use 30 to 60, and this range, as you see, it reduces here 10 to 15, 9 to 13.5, and so on and so forth. And average amplitude increases along this direction. This becomes lower, this increases along this direction, this increases along this direction. Radius of action increases along this direction. So this increases along this direction, and compaction rate also increases along this direction. So 80 to 150 you will be using actually mass concrete. Slump less than 50 mm, slump less than 50 mm, and this could be on basically relatively drier concrete, one may use this. So that's how one chooses the needle vibrator. Foam vibrator are external vibrators, transmits impulses both in plane and perpendicular to the foam. So what you do in this case, you have the concrete here, this is the concrete side of it. You put the foam vibrator here, right, and it is fixed. So it is fixed here, foam vibrator here. So as it vibrates, it transmits vibratory wave both in this direction as well as this direction, both in this direction, and causes vibration. So again, it will be rotating eccentric. So it causes foam to vibrate, right? So both in plane and perpendicular to the foam, it actually transmits the vibration. I deliberately didn't want to put in a figure because then I'll be going too much into the equipment part of it. Now, form is vibrated and vibration is transmitted from the form to concrete. Its acceleration generally ranges from 1g to 3g for adequate amplitude. Both rotary and reciprocating types are used and can be electrically or pneumatically driven. So basically you can have both, rotary type, rotary, and reciprocating type, and can be electrically or pneumatically operated. And you can see the RPM. So these RPMs, if you can see the RPM, kilocycles per minute is 6 to 12 kilocycle. There is 3 to 6 kilocycles per minute. 6 to So if you look at the earlier cases, so this is relatively large, higher side. On the higher side, for the larger needles, use the frequencies. If you can go back to the previous one, so you can see that. If you remember, this is, if we go back to this, the 10 to 15, the first smaller one was using, thinner ones were using high frequencies. So this is somewhere in between, right? So that's what it is. So this is form vibrators. Quite often we use them in thin sections. We use them in thin sections where we can't use really poker vibrator or needle vibrator. The first ones. So when we can't use them, then we can use this. Or when we are using them together with this is used. So form vibrators are used in thin sections. It's not the best thing. Thin form vibrators are definitely not the best of the kind of vibrators, because some of the energy will be lost in vibrating the form itself. So that's not the best one. Needle vibrator obviously does a much better job because it's an internal vibrator and go inside and compact the concrete. Thirdly, the vibration will be limited up to certain depth from the form only. The other kind of vibrator, that is table vibrator, vibrating table, are usually used for precast element or for laboratories. Frequency is less than 6000 RPM, vibrations per minute, and amplitude is less than 0.12 millimeter. So this is precast element can be used. For precast element, one can use this. Surface vibrators exert their effects at top surface and include, of course, the vibrating screed, pen type vibrator, vibrating roller screed, vibrating plate, and vibrating roller for pavement concrete. So they have their specific use for this surface vibrators. So we have seen where we select the needle vibrator of what dimension, right? Now we can look into form vibrators. Where do we select them? Where it's impractical to use internal vibrators, or it might be supplementing the internal vibrators. Vibrating screeds are used in thin slabs. High frequency and low amplitude vibration generally results in more efficient compaction. So that is what is the thin. The thinnest of the needle vibrator actually is most effective, but its radius is also low. So your effort in moving this will be relatively high. How does fresh concrete behave under vibration? Let us see. As we said, prior to compaction, concrete is a mass of separate particles coated with mortar, held in a pile by an arching action of coarser particles. If you can recall, it will be something like, if you can remember, it will be something like particles of different sizes and shape heaped up together, and you have actually mortars in between. You have mortar in between. So you have mortar in between. It's like a pile of material with mortar in between. So the red is the mortar, black is the aggregates. I have put it spherical aggregates, they need not be so. So the mortar should be somewhere there. So it remains like a hip. It's like a hip. Mortar held in pile by arching action of the coarser particles. So basically there will be arching action, one supports the other, and one particle supports the other. Now, as you this actually should be, it should be able to, it should move and get the shape of the mold. So what you have to do? You have to see that this particle moves downward, this particle moves downward, So you have to see that this particle has to move downward, this particle has to move downward and get the shape of the mold itself. So arching action of this one, they actually hold the particle because one particle is touching the other. So by friction, one particle is touching the other. So by the friction, they are just in position. So actually their fall due to gravity is restricted or obstructed by the friction between the particles. So you have to overcome this friction. And how do you overcome this friction? So one has to overcome this friction, and let's look at our next statement. The arching is result of friction between aggregate particles, surface tension of cohesive forces of cement paste. Of course, since it's a paste is in liquid or plastic state, it's in plastic state, therefore there's some surface tension and cohesive forces of the cement paste that will also held in position the particulate system itself in the heap. Now you got to overcome this. So this arching actually results in a void of air of about 30%, because these are the particles are something like this, and there is mortar, as I said. So but there will be air gap in between. So there will be air gap in between, there will be some amount of air gap. There will be some amount of air gap in between. So this air gap is about 30%. Air gap is about 30%. So you will have air gap somewhere in between this particulate system, and this air gaps are air gap, and they would be about 30%. 30% air gap would exist, and you got to dry this air out. So that is the idea. That is the idea of vibration. So what happens? Vibratory impulse actually liquefy the mortar portion of concrete, and thus reduce the internal friction, resulting in consolidation by force of gravity. Then once it is vibrated, concrete, vibrated completely, the friction is re-established and cohesion is restored and strength increases. Now how does it occur? So vibratory impulse essentially causes the water or the water particle in the cementitious system or paste system, which can vibrate more, which actually moves more than the solid particles, and more the constricted the necks are, it will exert more pressure, and this pressure actually overcomes the friction, resulting in a kind of collapse of the system. So the velocity of compression waves generated could be of the order around 45 meter per second in the beginning of vibration and increase to 240 meter per second at the end. So essentially liquefaction of the mortar occurs. That's because the water within the pore system would vibrate more or move more than the solid particles and cause an excess pressure in the system, and that reduces down the friction or overcomes the friction within the particulate system, and results in mobility or movement of the particle, and also drives out the air. For 200 hertz, the velocity, this corresponds to about, so wavelength is of the order of around 0.2 meter to about 1-2 meter wavelength. That's of course the thing. The waves moves water more than the solids. That's what I was saying, and generates hydraulic pressure within the interstitial water-filled spaces. And this pressure is maximum in most constricted space and causes reduced internal friction, giving the paste temporary fluidity. That's what I was just saying. So this water within the constricted space, because of the movement, it exerts pressure, and that overcomes the friction. And that's how the particle moves, right? That's how the particle moves. The process of liquefaction is easily understood through, let us say, box shear test, which we normally do in soil. Now, this kind of tests are also conducted in concrete long back, and one would see something of this kind. One would see something of this kind. For example, you have shear strain along this direction and shear stress along this direction. You have shear strain along this direction and shear stress along this direction and shear strain along this direction. Now you apply normal pressure, sigma n, and tau is applied from this side and strain is measured, delta divided by h. This is h and delta is this distance. So if you measure the stress versus strain, you find this sort of curve, and this depends upon sigma 1, sigma 2. So as you increase, the yield shear stress actually increases. So normal force, higher normal force, yield shear stress actually increases, higher normal force, yield shear stress increases. So concrete people have done box shear stress, and this is the kind of behavior which normally one would see. And then like soil, you can actually put shear stress versus normal stress curve, and this is your normal stress, this is the shear stress, and it can be related linearly. It can be related linearly like this. So therefore, tau yield shear stress is a function of tau 0 at this point, the intercept, plus mu into sigma, since this is a function of mu into sigma. So you see the yield shear stress is a function of yield. What is yield shear stress? That was this one, that was shown here, that was shown in the previous diagram. This is the yield shear stress. Yield shear stress, it increases with sigma. It increases with sigma. So as sigma increases, yield shear stress increases, and one can linearly relate this, simply linearly relate this, and this is tau 0 at 0 normal stress, and of course, this is the tensile strength of the whole thing, normal tensile strength. So mu is this slope, and sigma is the normal stress. Now mu is equals to 10 phi. Phi is what is angle of repose. So mu is equals to 10 phi, and that's the angle of repose. This we know in soil. This is what we see. So concrete, drier concrete almost behave like soil, and people have studied this. And shear stress strain relationship, this was before vibration if one measures. But supposing I measure this during vibration, what will happen is, if I forget about the drooping portion, the strain softening portion, for same sigma 1, sigma 2, sigma 3, stress strain curve is something like this, but when I vibrate, stress strain curve goes like this. That is, during vibration, the yield stress reduces significantly, and the stress strain curve becomes something like this. So if I may look at it again, this was the case prior to, this is mu, this is my mu, and this is my mu, and this is the tau y is equals to this is the tau y is equals to tau 0 mu sigma before vibration. And during vibration, what happens is, during vibration, what happens is, actually there is yield shear stress reduces significantly, right? Yield shear stress reduces significantly, and after certain period of time, you find that like yield shear stress actually reduces significantly, tau reduces significantly, depending upon, of course, sigma value. So my sigma, this is my sigma. So after an increase in the sigma value, you find that it behaves almost something not exactly parallel to this, but in some value like this. So when your sigma is applied, sigma normal is small, yield shear stress is for small sigma n, for small sigma n, tau y is small. During vibration, this is during vibration. So during vibration, it behaves like this. And up to certain sigma value, up to certain sigma normal value, practically there will be no yield shear stress. Now this is actually the sigma. This sigma value corresponds to actually equivalent force of vibration. What we call is this. We call this as, we define this as agitation pressure. So the agitation pressure, if the normal stress is less than the agitation pressure, which is actually the slope, if I extend this line, this is during vibration. So if I extend this line, this is the normal stress that will correspond to agitation pressure. So this is agitation pressure. So during vibration, it is like this. And you can go back to this diagram again, earlier diagram again. So this is agitation pressure here. So if your normal stress is more than the agitation pressure, then only you find that yield stress starts increasing. So the result of vibration, yield stress reduces significantly. But mu, of course, the slope of this one is more than the original. And after vibration, actually it stiffens, the yield shear stress has gone back to higher some value. Once you stop the vibration, it's because the cohesiveness is re-established, and that's how the behavior is. So it would again show up, it will show up the strength part of it. Same thing is shown here during vibration, before vibration, and after vibration. So this angle also increases. This angle, this is more or less similar angle. This angle is similar, while this angle is less. So actually your tan phi, mu sigma, so the tan phi actually has increased, angle of repose has increased. That means it can stand on its own more stiffer in a stiffer angle. And this diagram also shows you something like this. This is before vibration. During vibration, you start vibrating, yield shear stress comes down very significantly, and then you stop, again it re-establishes itself, and that's how it is. So basically, when you vibrating, yield shear stress come down. Therefore, particle can move. Shear, movement due to the shear force can occur. It can move over each other or slide over each other. Shear flow would be occurring actually, and then due to this, the air will be driven out, and it can get the right kind of shape of the mold itself. So that's the mechanism of vibration. That's the mechanism of, so fresh concrete consolidation actually occurs in two phases. In the first stage, vertical settlement of coarse aggregate takes place in a manner similar to packing of granular material, and shape of the aggregate plays a major role. Air voids up to 5% remains after this. Spherical particles will actually easily roll over, and therefore, the first stage itself, vertical settlement becomes easier for rounded aggregate. Then you have, at the end of the second stage, concrete behaves like dense liquid because the air voids have been removed quite a bit, and finally air voids are removed from the surface, forcing mortar to appear at the surface. So this is important. To understand or know that mortar will appear at the surface. Once the air voids moved out, the mortar will appear at the surface. So once you have first phase is over, second phase actually mortar will come out, and that's also a test for whether the vibration is complete or not. You'll find that a slurry or mortar phase is coming out at the top, and then you can stop vibration. One can measure the unit weight by various density gauges, and they typically look like this: unit weight, time of vibration. So this is your time of vibration and unit weight. So after a certain period of time, vibration is complete. In fact, somewhere here the mortar would have come out right at the top, and after that you need not look into any further, the vibration is over. What you shouldn't do with respect to vibration, you see, this is the correct type, this is incorrect. So needle vibrator should not be penetrated in an angle. This is incorrect, this is correct, because they will be dragging the concrete along this direction. So by and large, it should be vertically put down. And if it is on a slope surface, it should be done, from this, the concrete is over. There is, here you place it, so you do from the bottom and go upward. So it is desirable that one does vibrating vertically downward without the inclination of the needle. It is not desirable to incline the needle and do it. And one should not push the concrete by vibration like this being done here. So that's some do's and don'ts with respect to vibration. It should not be moved using internal vibrator, and which can result in segregation. That means penetrate vertically to sufficiently embed in concrete, held stationary, and remove slowly, say 7.5 meter per second, centimeter per second is a good velocity, slow velocity, but one may not be measuring them. But the idea is that when you are taking out the vibrator, it should be taken out slowly. It should be done at regular spacing to ensure compaction of all portions with adequate overlap. There should be adequate overlap. I mean, typically it should be like this. If this is the radius of action, which is known for types of needle that we talked about, the second one, needle location will be here so that there is the right kind of overlap. So this is the overlap. So overlap should be like this, overlap. So right kind of overlap should be there. In other words, if I have sections like this, where I have one circle covers it, or thinner section, it covers maybe something like this. The next one should be something like this, and so on. So that overlap is here. Overlap is here. Next one should be something like this. So there should be sufficient overlap. Sufficient overlap, that's the idea. There should be sufficient overlap. Right? There should be sufficient overlap. That's the idea. No left portion should be left blank. Minimum usually 10 seconds is necessary for complete compaction. Vibration time needed is given by some equation. I think I am not talking about that. I am not talking about that because equations nobody is going to use it much. But we understand that at least 10 seconds if you keep it, and when you see the mortar has come out, mortar has come out mortar has come out, you pick it up, pick the needle vibrator, just lift it up slowly at a very slow velocity, and you can see the slurry right at the top. For, of course, shutter vibrators, which are fastened with the foam, vibration time is 2 minutes to 30 minutes depending upon concrete and vibrator itself. So they require longer period of time, more energy. Screed needs, of course, 2 passes. And degree of vibration achieved by surface vibrator, of course, one can see from the figure that is there. Actually, up to only certain depth, vibration is. So it's about something like about 8-10 centimeters from the top, which means that 80 mm, and not really much. After that, the density reduces down. So it's only the top portion maximum can reach, you can actually vibrate. Similarly, shutter vibrator also will not go throughout the section if the section is thick. So that's what it is. Right. Now, imperfection in vibrators, honeycombing. Actually, it should be in vibrations actually. In imperfection due to poor vibration, essentially. So in vibrators is not the one. In vibration, you can say concrete vibration. Honeycombing, if you have not done the vibration properly. But it can have, it will have stony and air voids. Can generally happen in narrow sections, and grout loss can also cause this if the forms are not joined properly. Free fall, low slump concrete, this is a concrete type, and poor vibration can result in this. Well, blow holes or bug holes, which you see normally in concrete, small holes, aesthetically ugly looking. Excess form oil, if you are using, you can have this kind of thing. Lean and low slump concrete, you get it, and of course inadequate vibration. So poor vibration can result in honeycombing. Inadequate vibration can increase the bug holes formation. Bug holes are pretty common, they are not very harmful, but they look very ugly. Not a good finish. Subsidence and cracking, of course, this can happen due to plastic settlement. Now it's a bleeding concrete. This can occur in concrete which is bleeding, because which is bleeding, the water comes up and the solid subsides. So this can happen, and inadequate vibration can result in this. High water content is usually the concrete cause which can do it. So in high concrete which has got high water content, you might get short cracks. The cracks looks like this, in fact. Sometime we might be discussing. Over reinforcement, sometime you might see. Just over the, this is the concrete. In fact, if it might look something like this. So the top concrete surface might look like this. There is a crack, and then there is a subsidence, there is a crack, and so on and so forth. So you have reinforcement here. This is a concrete surface. This is concrete. So in the concrete surface, so let me draw it just here. Let me just here. It can look like this. This is, then there's a crack. then there's a crack. This usually, quite often, could be over reinforcement and then several other situations. This is my concrete. So this is a slab, large slab, and similar sort of situation. You might see some plastic settlement cracks just over the river, just over the river. Just over the river. You might see them just over the reinforcement bar. So this is plastic settlement crack. It comes when your water is too high. Plastic settlement crack. Plastic settlement for high water content and inadequate vibration. So where you have high water content, if you have done inadequate vibration, you might still get this. In fact, inadequate vibration is also a cause, not the primary cause, but it's also a cause, you can see. Form of set, of course, it has nothing to do with the vibration. So I'm not just, if your form have not been bolted properly, this can result in defects. Cold joints formation, that's also inadequate vibration of the lower level. Cold joint occurs when you have one concrete, old concrete, and then you have new concrete, which is over here, new concrete. So there can be cold joint formation, and this is inadequately vibrated. You might have cracks coming in, or weak joint forming here if it is not vibrated properly. So that's it. These are the defects which can come for vibrations, imperfections that can come from vibrations. Special vibrations are vacuum vibrations. Revibration can be done as long as running internal vibrator sync. So if your internal vibrator, if it sinks into the concrete, and penetration resistance of around 3.5 MPa. Now penetration resistance is a measure of setting. Penetration resistance is a measure of setting, and it should be 3.5 MPa. If it is more than that, then you cannot use it. Can increase strength, bond, impermeability, reduce shrinkage, and creep. So revibration is not desirable, but you can do it. If it is to be done, you can do it as long as the concrete is not set, and it's measured by penetration resistance. Vacuum vibration is accomplished by applying vacuum to surface of fresh concrete. Cement paste is densified by removal of air from the surface and water from the certain depth. Now this is applied where vacuum dewatered concrete, floorings, abrasion resistance, high abrasion resistance, like warehouse flooring or industrial flooring. So this is done where you are likely to have a lot of abrasion. Basically water is removed. This water is used for placing the concrete, but it is removed, so water cement ratio is low and you get relatively strong concrete. So placing concrete with higher water content by extracting extra water, then you extract the extra water. So in strength is improved, commonly used for slabs, walls, vacuum between 30 to 50 centimeter of mercury applied by means of special liners of material which you allow water to come out, but the solid will keep. So you have a mat placed on top of the concrete, and then water is evacuated out. It's through the vacuum, water is taken out. It should be applied as early as possible. Penetration of vacuum is up to about 30 centimeter, is less efficient in air entrained concrete because then air will come out. Fresh mix subjected to high frequency vibration over 100 Hz is called vibro activation, increases the strength by intensifying hydration, generally does not have anything to do with compaction. So if you have used high frequency vibration, then hydration process increases, nothing to do with the compaction. Right, so these are special cases. Now let's look into the second part of our discussion, that is curing. Hydration reaction is not instantaneous. It's not like an explosion reaction which is instantaneous. So it occurs over a long period of time, and therefore water must be available for hydration. Now for hydration to continue, you need a relative humidity of 100%. Besides, there will be loss of water by evaporation, and it shall be prevented. And if you can't prevent it, it should be replenished. You may not be able to prevent it, so it should be replenished. Then somewhat water will be consumed by the chemical reaction itself. So what we call is self-desiccation. And this also got to replenish. So essentially what happens is reaction requires longer period of time and occurs at only 100% RH, so you must maintain 100% RH. Water by loss of evaporation, loss of water by evaporation occurs, and that has to be replenished to maintain 100% RH. And self-desiccation also would cause some water loss, and that should be also replenished. And also sometimes maintain conducive temperature. So this is the purpose why you need curing, need for curing. Well, most important is if you don't do this, if you have inadequate hydration occurring, the capillary pores in the system, which we have discussed earlier, if you can recollect, we have discussed earlier sometime, cement, between cement hydrates, outer product, etc., and you will have unhydrated cement system. Unhydrated cement is somewhere there. Then there will be capillary pores, interconnected capillary pores in between. You will have capillary pores. So these capillary pores, which we have discussed earlier, they need to be segmented. Now, only when you have sufficient hydration product, they will come and touch each other from both the sides, and capillary will get segmented. So minimum curing is required in order to ensure that capillary gets segmented. Otherwise, unsegmented capillary will result in poor durability of concrete. So if you have not done good curing, what will happen? Obviously, strength development would not be there because hydration has not occurred. A lot of pore space will be remaining, and drying shrinkage can result because the water has gone out, so it can cause drying shrinkage, and this can result in cracks. May be aggregated by high ambient temperature and low relative humidity. Poorly segmented capillary results in lower durability of concrete. So this is what is the effect of curing. Now, how do we do curing? We do moist curing. Supposing I got a water cement ratio of 0.5 concrete, and if I cure it continuously submerged, this is continuously submerged, the strength will increase in this manner. Give it 28 days cured, strength will increase in this manner. 14 days cured, strength will go like this up to 14 days, and then it will flatten out. So 28 days, strength will increase nearly up to, or 20 days a little bit, then it will flatten out. Continuously moist cured will go like this. Continuously in air, of course, strength development will be much less with time, and 3 days, so up to 3 days, there will be increase slightly more than 3 days. So what happens is, when you have stopped curing, after that hydration proceeds for a little while, and after that there is no further strength development. So therefore, strength development I need. Compressive strength is a function of curing age. And if I continuously cure it, moist cure it, continuously moist cure it, then this is what I get. It increases significantly, continuously it will go on increasing. So that's what it is. For strength gain, I need some amount of minimum curing. More the moist curing I do, I will be gaining this. Strength will be gained, concrete will be gaining this way. Methods of curing, obviously water curing is the number one. Ponding, spraying, that's how you do. You just, if it is a slab like this, if it is a slab, concrete is here. So you make some sort of a barrier here on both these sides, and simply do, ponding. Simply do ponding. So you have ponding, water here. Water is, so these slabs you can actually do ponding. Ponding can be done on slab. Spraying, spray with any kind of pipe, and then covering with wet sand. So instead of ponding, what you can do is you can just put in sand particle here, and this has to be maintained wet. Or you put wet Hessian clothes or absorbent covering. So this could be for slab or for columns also. For example, if it is a column, you can put actually wet Hessian. You can put wet Hessian here, Hessian clothes here, which will remain wet all the time. So you keep it wet, with some kind of absorbent covering. So this is one, moist curing is done in this manner. Then you have got foam retention and covering concrete prior to setting. Of course, you can retain the foam, but that will not be replenishing the water. or cover the concrete prior to full setting or even after that. So water actually will not go away, but at the same time, it will not replenish the water. Membrane curing, basically you apply resins and waxes on top of the concrete to form a membrane. It can be sprayed or hand brush applied, let us say. So that what it does, it will see that no water goes out. Whatever water is inside, that is used up. So no evaporation. So both second and third, this one and this one, they will ensure that there is no loss of water, but then there is no loss of water, but then they will not replenish the self-desiccation water. So these are the methods. Then you have steam curing. Waterproof plastic sheeting some people have used, and steam curing. Steam curing is used where you want to get accelerated strength. Maybe pre-stressing you are doing, so you want to do the pre-stressing quickly, and that's where you use this. Moist curing. If you see compressive strength, you can compare the compressive strength. You see 28 days, this side is for different water cement ratio. So you get, the comparison is ponded and Hessian. So this high one is ponded, this is Hessian cloth, this is Hessian cloth is somewhere here, Hessian cloth is here, ponded is there. So Hessian, ponded. So ponding does a good job, actually, ponding does better job, ponding is here, and Hessian is relatively less, Hessian is lower one. So Hessian is lower one, and this is for 1 day, this is for 3 days, this is for 28 days. So ponding does a better job than Hessian, or putting an water absorbing cloth or something covered. So cylinder strength, okay, basically what we want to see is the qualitative, because quantitative values doesn't make much of a sense, it will vary from concrete to concrete. So Hessian, ponding is a good thing when you have the facility, and also there is a possibility of doing. For example, you can do ponding on slabs or horizontal members, particularly large horizontal members, but you can't do it on columns. Curing by formwork covering membrane, of course, stops evaporation, which I said, but do not replenish the moisture loss due to self-desiccation. That's a problem. Now, you need a minimum days of curing for segmentation of the capillary, and it depends upon water cement ratio. For example, water cement ratio 0.4, it is just 3 days, and for water cement ratio 0.7, it may take 1 year. So higher the water cement ratio, more days are required to segment the capillaries. It's understandable, because more higher water cement ratio, larger size will be the capillary pores and more will be the capillary pores, and they will be more connected. They are beyond percolation threshold, so all of them will be connected. So code actually specify minimum curing days based on this. For example, Indian code says that 7 days minimum curing is required for ordinary Portland cement, but if it is pozzolana blending, then you will need 10 days in normal weather, but correspondingly you will need 10 and 14 days in normal weather, and of course dry weather like desert areas where it's more dry, there you will require 14 days when you have pozzolana blended cement. But pozzolana blended cement, or they will require more number of curing days for strength development, because that process is slow. So that's what I was saying, IS 456 recommendation, at least 7 days for OPC, 10 days for blended cement, concrete with mineral admixtures in normal condition. But for dry and hot condition, these periods are 10 and 14. Other codes are actually much more elaborate. I don't have time here to talk about those. They are much more elaborate. Some of them would talk about the curing depending upon water cement ratio, also the kind of evaporation losses possible, air velocity. There's, for example, erstwhile British code was quite elaborate in this respect. Our code is much more simple and simpler. Okay, so that's what it is. What about temperature? Concrete cast and cured at the indicated temperature. Let us say this is basically temperature is 30 degrees centigrade, 1 day, age. So age, and this is 28 days. So if you cure it at, let us say, 10 degrees centigrade, strength is here, 20 degrees, strength is here, 30 degrees, strength reduced, 40 degrees, strength reduced. So if you look at 20 days strength, cure it at 40 degree will be less strength than cure it at somewhere around 20, 22, 23 degrees. Similarly, 3 days strength and so on and so forth. So it actually, higher temperature, early strength gain is high. It's almost close to that. Higher temperature, early strength gain is high. But later 28 days strength, it actually reduces down. So maximum 28 days strength you are getting at 20 degrees centigrade when you are casting and curing at the same temperature. All right. Now we talk in terms of something called maturity, temperature effect. What has been seen is that T measured about 11 degrees centigrade, and if you for let us say T1, delta T1, so it was maintained at delta T1 for delta T1 time, T2 for delta T2 time, etc., etc., and sum this up. This is what is called maturity, and it has been seen then maturity log scale degree centigrade days versus compressive strength can be really linearly related. So higher temperature, lesser time, you will get almost same effect when you have lower temperature and longer period effect. That's the idea, and that gives you the idea about steam curing. That gives you the idea about steam curing. So we'll just look at steam curing. Steam cured concrete, if you apply immediately after, if you apply immediately after, strength gain is poor. But if you maintain it at 74 degrees centigrade, you are somewhere here in this curve. 54 is somewhere there. 31 is somewhere there. 91 strength gain you don't get. So compressive strength at different age, it is given hours, 72 hours, 3 days strength. So somewhere around 74 or so degrees centigrade, you get strength, good strength in 3 days. If you are looking for very high temperature, doesn't give you very high strength. Generally, steam curing, steam at atmospheric pressure will have low, it will have about 75-80 degrees centigrade. So what you do is you don't apply immediately, because then strength gain you don't get. So there is a delay period. This is the delay period. Then there is a steam heating period. Maintain that temperature, supply the steam and maintain it, then cool it. So basically something like 5 to 20. So if you do it for about 15 to 20, 15 hours, 13, 14 hours of steam curing, you can develop, this is the kind of practice that we do, we get good strength. All right. So steam curing is something like this, typical steam curing cycle. And this is if you are trying to get early strength. So we can summarize now. Basically, we have looked into all the methods of compaction, and then the mechanism, how the compaction occurs. And lastly, then we looked into curing, the methods of curing, need for curing, importance of curing. That's what we have highlighted. One thing, the curing is very important from durability purpose, which people quite often ignore. It's good for strength development, but the minimum curing is absolutely essential for durability. We quite often try to, you ignore it also because of the kind of practices that you have. If it is a sprinkled one continuously in a precast factory, that will be good curing. But in situ, when curing is done, quite often it is ignored. It would be the most unskilled person would be doing it. Now, such curing do not help the system. The strength will be lower, durability also might be affected. Another contractual problem is in Indian scenario, curing is always part of concreting. So obviously it is not a separate item. So therefore also the strength development. So that's all as the summary, and summary of also the module 5, where we have looked largely into the fresh concrete issues and concrete production process. The curing completes it. Thank you very much.